Broadcast is now starting. All attendees are in listen-only mode.
Hi, we'd like to welcome you to another in a series of webinars designed for departments of transportation. I'm Terry Bills, and I'm the Transportation Industry Manager here at Esri. And today I'm joined by Paul Durden and Andrew Wilson, both of Abley Consultants, one of our business partners based in New Zealand. Today's webinar is the third in the series that we've done with Abley, who we think is actually doing some very important and creative work in safety with GIS. The first webinar focused on out-of-context curves and how we can use GIS to identify dangerous curves, road curves using GIS. The second webinar focused on identifying dangerous intersections and identifying risks based on a few critical roadway infrastructure variables. And today we focus on a unique methodology that Abley has developed to allow DOTs to identify areas for no passing zones and to identify needed earthworks to improve safety and visibility along roadways. If you did not catch the first two, you can find them at our website, and we'll give you the link to that site at the end of the presentation. Before we begin, I'd like to point out that we're recording this webinar, and while everyone will be on mute, there will be time for question and answers at the end of the presentation. So you can type your questions into the question box, and we'll try to answer as many as time allows. Additionally, these slides, which are part of this webinar, will be available to you on the GeoNet group, Departments of Transportation, and we'll also give you that link at the end of the webinar. So I'd like to start out with a little bit of a repetition from our prior safety webinars because I think it's important in understanding the approach taken by Abley and their safety work. And in the past, and especially here in the US, much of the focus of safety management was often on changing driver behavior and driver education programs. But in the late 1990s, independently, both in Sweden and the Netherlands, they began to take a different approach. In Sweden, it was the Vision Zero approach, which was officially adopted in 1997. And in the Netherlands, it was the Sustainable Safety Program. And that became the dominant approach in the Netherlands in the same year. And both started from a much different starting point. Really from an ethical position that human safety should be the top priority and that traffic deaths are ultimately preventable. They recognize that humans make mistakes, and as a result, we really need to focus on better highway design and ultimately by making our roadways more forgivable to human failure. And while each approach took a holistic approach to road safety, each represented a fundamental shift away from the prior safety paradigms. And major initiatives that have taken from these concepts include the UN Decade of Action, which is now worldwide, Vision Zero, which, as we mentioned, originally started in Sweden, but now has been adopted by a number of US cities and states, and the US DOT, their own initiative called Road to Zero, which was initiated in 2016. And I'd like to point out the great success that this particular approach has had in Europe. As I've pointed out in the past, in a 5-year period, Norway was able to reduce road fatalities by 43%, Greece by 36%, thus pointing out what a highly focused initiative can really do for highway safety. On the other hand, the US has fallen to 30th in road safety, measured by fatalities per 100,000 people. One of the examples that I often use is that in the 1990s, Slovenia had a fatality rate 5 times higher than the US. Today, however, they're roughly twice as safe. So we start with the recognition that road safety is a function of political will, and some countries have been able to make significant improvements in very short periods of time. And had we followed the European trajectory in road safety over the last 20 years, we would have saved 20,000 lives a year, according to a recent study. Key tenets of the Vision Zero approach include, as we've said, that traffic deaths are preventable, and that taking a strong focus on highway safety is an ethical concern of the highest order. Every traffic death should be prevented. In addition, there are also social equity concerns that we should have the same focus and investment for every life. And finally, that a Vision Zero approach is ultimately a data-driven approach, that we use data and monitoring activities to continuously refine our approach to achieving zero deaths. Because safety is such a critical issue, we anticipate having many more webinars on this topic in the future. I hope that we can make this forum a forum to share best practice and to bring to you some of the best thinking with respect to safety management. So with that, let me turn it over to Paul to present some of their leading edge safety work. Paul, over to you.
Thank you, Terry, and welcome everyone to the webinar. So as Terry said, I'm here with my colleague Andrew Wilson today, and together we'll be speaking about two projects that we've been working on in New Zealand that are directly applicable to any road controlling authority throughout the world. They're largely around targeting safety interventions and helping progress ahead from simple risk analyses to guiding transport practitioners in identifying the most suitable countermeasures they may wish to introduce on the network. So the first of those is centred on a project that we've conducted for the Northland Transportation Alliance, and it's very much born out of the fact that road controlling authorities, particularly at a county level, are very resource constrained, often have staff who are performing multiple roles, and can find it difficult to set aside time to plan their safety programs in great depth. So this project that we've conducted for the Northland Transportation Alliance, which is situated right at the northern tip of New Zealand, comprises of three county areas: the Far North District, the Whangarei District, and the Kaipara District. The population there is around 150,000 people, and they collectively manage a road network of 7,000 kilometres. That's about 4,500 miles. And in the last 5 years, there's been around 2,200 injury crashes. So over a number of years, we've developed a series of risk mapping and intervention tools for the Northland Transportation Alliance using ArcGIS tools. And today we'll be talking about three components of that. So one is how we have presented a web viewer that combines and displays data from a myriad of sources. Second one is some work that we've been doing to enhance the interactiveness of the data for practitioners, and then progressing on to the safety programming element. So what's already been done? Well, annually we generate what is called KiwiRAP crash modelling results, crash risk modelling results, and that's where we look at risk across a network for intersections and corridors. We update those metrics annually and are able to identify change in those metrics on an annualised basis. We also generate active road user heat maps, and at a national level, we have assisted the New Zealand Transport Agency in developing a very large number of road safety metrics, particularly around speed management. And elements of that include infrastructure risk rating, which is a proactive risk analysis method, calculation of safe and appropriate speeds, the identification of the highest benefit opportunities on the roading network for reducing death and serious injuries, the out-of-context curve and speed modelling analyses, and Terry touched on that before. That was a webinar that we conducted back in January of this year. And we combine all of those data sets into a web viewer for the Northland Transportation Alliance, and I'll briefly show you some screenshots from that at the moment. You can see the layer list down the right-hand side. Here we're showing the aggregated corridors and the risk levels there. Just for everyone's benefit, green is lower risk, yellow, then orange, red, and black is the highest level of risk. Here we're looking at functionality that allows just the high and medium risk sections to be identified within the web viewer. We've got the intersection analyses as well, so we can see that there are some high risk intersections in this area. We have other specific analyses. This one here is focused around crash commonality at intersections, and what this one here shows us is that there's a commonality in crashes happening at this particular intersection we've highlighted, where 4 out of the 6 injury crashes are attributed to red light running crashes. In terms of the heat maps, we can see that the vulnerable road users or active road users, that's pedestrians and cyclists, tend to congregate around the urban areas. And if we zoom into Whangarei, we can see the clusters there happening around the main parts of the network in the town centre area. Here we're looking at the prioritised high-risk corridors in terms of curve risk, and we have those corridors there. And at the same time, we can then overlay the individual curve analyses over top of those as well. Bringing in the national data sets, here's the infrastructure risk rating. So this is the proactive risk. This one is independent of crash history, but looking at the underlying level of risk across the network. And we can see that there is a very high level of risk across the network, but that contrasts very significantly with the earlier risk metrics. And the reason why that is much of this network of roads has very, very low volumes on it, and simply we don't have enough traffic using the roads to have confidence that actual safety performance is a very strong indicator of actual risk. This one here being a much better predictor of risk. Looking at, sorry, I'll go back a slide, safe and appropriate speeds across the network in terms of prioritising for speed management. And then we've got identified high benefit opportunities from the national analyses that are saying these are the roads where we need to prioritise our investigations for speed management, and speed management being potentially a review of the speed limit or investing in the road to bring the standard of the road up to an appropriate safe level to support the current existing speed limit. And we can overlay different data sets and look at different metrics in combination. So that's the crash viewer component. One of the things that we've now done is also develop using custom web app builder widgets a number of crash boards and crash filters. So this one here shows a crash filter that we've developed for the Northland Transportation Alliance that allows users to filter crashes by severity, road user involvement, day or night time, what are the factors involved, whether it was speed, alcohol, was the road wet or dry, and the movements as well. So this has been found to be particularly useful for the safety staff in the Northland area. We've developed a crash board as well, so that allows users to select a corridor or an intersection, and then that, using the web app builder widget, retrieves the crashes that are associated with that particular corridor, and we've created simple charts. So we have a pie chart up the top right-hand corner there that shows the distribution of crash types along that corridor. We've got a total of the number of injury and fatal and serious crashes, and then a simple histogram showing crashes, how that is varying on an annualized basis. So this is, again, just adding that extra layer of detail into the web viewer. Now, what we've done now is taken this to the next step, which is to really provide guidance for the Northland Transportation Alliance around, well, what should I do specifically? Can you help us and develop a tool that provides that next layer of guidance and gives us some ability to identify likely suitable interventions and allow us to build our own program from there. So we've called this safety programming on the fly, so to speak, and I'll show you how that works. So what we've done in the first instance is we have utilised resources from New Zealand. So we have high-risk guides, so we've got a high-risk rural roads guide and a high-risk intersections guide, and within those guidance documents, they contain crash modification factors or crash reduction factors. We've collated all of those for different treatment types, and we've assigned those to different parts of the network depending on a very wide range of factors, including the functional classification of the road, whether it's urban or rural, and also the risk profile and risk attributes of that section of road. And that's all stored away in the background, and we have a number of decision trees that are used to identify suitable treatments depending on the part of the network that's selected. So here you can see the interface for the safety programming tool, and it allows users to either select a corridor or an intersection or to define their own custom start or endpoints. And look, we have used a geometry engine and ArcGIS API for JavaScript to develop the customized start and endpoints for this particular one. So if we select a corridor here, you'll see the corridor is highlighted and the corridor details are populated with relevant metrics around that particular corridor. You can see there is the ONRC is one network road classification, as we call it in New Zealand. That's our functional classification, risk profile, type of environment, speed limit, out of context curves, treatment philosophy, crash details around a number of crashes per that are occurring along that selected corridor. Then at the bottom we have a button that says Launch Safe Interventions, and the user clicks on that. And just before I get to that, and this one here shows the ability to customize by dropping points on a map the length of the corridor they're interested in, and you can see that some of those details on the right-hand side change because we've selected a shorter corridor that's customized specifically for the length of interest. So once we launch into the Safe Interventions component, it's populated with treatment options that are potentially suitable for the road environment that has been selected. It's pre-populated with crash reduction factors, but they are editable by practitioners depending on their own specific experience or expectations with that particular road. We do set limitations on how far you can modify those, and so for instance, a wide traversable median has a default value of 45%, and I believe for that one there, the acceptable range would be between 30 and 55%. So if a user was to try and enter a value outside of that range, that wouldn't be accepted in the proposal. We then have an estimated death and serious injury savings per annum associated with each of these potential interventions. The practitioner is then asked to enter a cost of implementation, and in the background that will calculate a BCR, which is a benefit cost ratio, which looks at the return on investment for particular intervention types. We've integrated with Google Street View as well here, so users can see the road environment from their desk if they're unfamiliar with particular parts. This looks at one of the corridors that were selected before. It's a winding environment, winding coastal environment, where we've got steep embankments on one side and relatively unprotected edge adjacent to the coast. So, as I said before, users can enter cost of implementation, see the relative cost effectiveness of different treatments, and they can select one or more of those treatments to push through into a program. So we have programs that they're able to develop and push these potential projects through to those. Once they've been pushed through into a program, the programs can then be viewed through the web application, and we can arrange prioritization of these by a number of factors, including prioritize based on benefit-cost ratio, prioritize based on deaths and serious injuries likely to be saved, so on and so forth. The controlling authority can also set their program budget, and that can be used to identify which projects would be able to be achieved within the program budget and which ones would fall outside of it. It's also downloadable to a CSV format so that they can introduce the outputs of the program into any internal or external reporting requirements they have. So that's the Northland Transportation Alliance tool, the safety programming on the fly. It brings together the myriad of data sources from both Northland and at the national level, and we've got all of that spatially displayed in one location. We've introduced interactive components with the data through the crash filter and crash board widgets, and we've created simple, high-level insights for local roading practitioners regarding the countermeasures that are most likely to be successful for parts of the network they're interested in. So that concludes that part of the presentation. What we're now going to move on to, and what Terry mentioned earlier, is an approach for sightline analyses and visibility assessment that we've developed. And we call this the ABLI CFVM, the Continuous Forward Visibility Model. So the Continuous Forward Visibility Model is an analytical process that we've developed that evaluates available unbroken sightline at regular increments along a road centreline. It assesses sightlines in a specified direction of travel based on configurable options. So today, the configurable options that we'll present to you are based around 100 feet of forward visibility, which is the sight line or the forward sight distance required in a 60-mile-per-hour zone. We've set the observation height at 1.1 metres and the observation target height at 1.25 metres, and the sampling frequency along the centre line happens every 2 metres. So we perform viewshed analyses that identify site limitations arising from conflicts with the road surface or the surrounding terrain and roadside environment. And it's a 3D spatial model built from high-resolution data sets to replicate the existing environment as closely as possible. So in terms of input data and software, the key data sets that we require here are an accurate centerline that's rich with attributes. We're able to add in some of our previous analyses, ABLI road safety metrics, curve context modelling. The key input here really is LiDAR surface modelling, and what we'll present to you today is around how we're able to use LiDAR data to generate this analysis. We've also combined high-resolution aerial imagery and point cloud data sets. Now, this project has been developed within an ArcGIS Pro environment where we've been using FME. Now, in terms of FME, this operation can be run in Esri's interop extension, and the data is displayed visually in Autodesk InfraWorks, or it can be displayed in ArcGIS Pro portal, ArcGIS Online. So why develop a continuous forward visibility model? Well, really, it's to reveal more about the nature of the existing road geometry and surrounding environment, and the aim is to produce a detailed data set about existing roadside features and visibility. This analysis can complement other work that's undertaken by roading authorities, and for our work, it can complement our Safe Curves work, and also can be matched in terms of assessing alignment with crash records and history. It's intended to aid in recommending treatments to improve safety outcomes and to investigate the impact that a policy change may have on a corridor. As I said before, this is a highly configurable product that we've developed, so we can change the forward sightline visibility requirements, speed of the road, so on and so forth, where the view position is within a vehicle, the height. Are we looking for identifying hazards actually on the road surface or at a point above the road? It's very accurate. It's built to resemble reality, and we've undertaken site field validation tests to confirm its level of accuracy. It's scalable, and it utilises cloud-based computing capabilities to produce analyses on short sections of corridor right through to entire road networks. And it's flexible. Hey, the model can readily ingest other data sets to complement analyses such as historical crash data, context-specific data, and inputs from other safety models. So in very simple terms, the process sets observation and destination points along the road at a defined length, and that's defaulted to every 2 metres. Observation rays are calculated between observation points and destination points, both with separately assigned distances above the ground. Points are created every 1 metre along the ray, and they contain a Z value at that location. That is compared to the surface model. Points below the surface are intersects and indicate an obstruction of view, and we're able to calculate around 24 million points per minute. So let's have a look at what this looks like in practice. So on the screenshot here, we can see on the top right-hand side a view from inside a vehicle as part of the field validation exercise, and on the left is the imagery that has been created from the high-resolution imagery as well as the LiDAR data. And then we have a plan view at the bottom that has the ray analyses that is looking ahead. Now, from this very point here is the point where our 1,000 feet of forward visibility is achieved just around the corner. You can see the embankment there permits forward visibility to occur. If we progress to the next slide, this is taken from an oblique angle slightly back from the previous location, back and up to the left. We can see the dots analyses here. So the orange dots indicate insufficient visibility is available at that every 2 metre interval, and then right at the point where the vehicle is located, the 1,000 feet of forward visibility commences and it becomes green. So let's have a look at some examples of the field validation that we have. Just bearing in mind that in New Zealand we drive on the left-hand side of the road, so if you're wondering why we're sitting on an unfamiliar side of the road, that's the reason why, but there's no reason why this analysis couldn't be conducted from for a right-hand drive network at all. One of the other things to bear in mind in New Zealand is our practice regarding no overtaking lines is that no overtaking lines are only marked where visibility or forward sight visibility is lost due to vertical terrain. So if forward visibility is lost due to a horizontal curve, the New Zealand policy is not to mark no overtaking lines. That is expected to be self-explaining to the driver. Now that's currently up for consideration at the policy level, and our model is being used to inform discussions around both safety and overtaking implications of exploring that policy change. Now, just in terms of these examples here, if you look closely at the bottom images, which are created using the high-quality aerial and LiDAR images, you'll be able to see a red line in the centre of the road, right in the distance. That indicates that there is no forward visibility available at that point, so forward visibility is lost due to either a vertical or a horizontal obstruction, either within the road environment or outside of the road. Now, those examples were in locations, I'll just flip back to that, in locations where no overtaking lines were installed. But what our analysis is showing is for the corridor that we've investigated, there are other instances along this road corridor where forward visibility is lost due to vertical terrain, but that is not captured or reflected in the markings that are on this corridor. And part of the reason for that is the way road controlling authorities assess no overtaking lines where they're supposed to be implemented at the moment is exceptionally manual and highly subjective and relies on people in the field making those assessment calls. And what we're saying is we've developed a model and a product that allows you to identify where that visibility is lost due to either vertical or horizontal visibility constraints. You can see that the model actually highly replicates the built environment and the physical environment with the trees and the natural contours of the road and the environment as well. Moving ahead, we can see these locations here where forward visibility is clearly lost, and that's replicated in our models and also reflected in the no overtaking lines on the road. And we have other analyses here. Example 8 shows that on occasion we do have issues with the quality of the LiDAR. In this instance, this part of the road passes through a cutting, and there are trees overhanging the cutting as well. So it gets a little bit messy in terms of processing the model, but nevertheless, it still says this does not provide safe forward visibility, and that's certainly the case at that point. So that is the level of validation that we've undertaken. That's what it looks like in a 3D sense. In a 2D sense, we can conduct the analyses and present it on a map and identify all of the instances along the road corridor where 330 metres or 1,000 feet of forward site visibility is not achieved. We can also identify whether or not the forward visibility is lost due to vertical terrain or through surroundings, meaning it's lost due to horizontal alignment, or whether it's lost due to both. And the analysis is directional. So previously we were looking in the west to east direction, now we're looking east to west. And this particular location will see that visibility is not achieved in one direction at the point that's highlighted here, and that might indicate the ability to conduct earthworks to remove the slight crest in the road that would create a much longer section of road that would be available to passing along the corridor. And this one here showing, again, analyses by vertical or horizontal restrictions along the corridor. So look, just in summary, this is a very customizable product that we've developed in terms of observation and target heights. The site distance requirement can dynamically update as a function of operating speeds and changes in grade. It's useful for examining areas that may be considered for minor realignment or regrading to create and extend overtaking opportunities. And very much, it's an excellent way to add value to existing LiDAR and DSM data sets. So we know that there is a lot of energy and money being invested into collecting LiDAR for a wide range of purposes. This is an analytical technique that can add value to that LiDAR that's being collected right across transport networks at the moment. And it may be used to inform corridor modelling to evaluate average number of passing opportunities per kilometre, per mile, adjusted for traffic volumes and traffic class such as heavy freight or caravans, camper vans. So that concludes our component of the presentation. I understand that Terry has been collating any questions that have been coming through with the webinar, and Andrew and I are here to answer those now for you. Back to you, Ray and Terry.
Okay, thanks, Paul. Appreciate it. That's there we go. We do have a number of questions that came in. Several questions really about whether the webinar was being recorded and will it be available after the fact. Yes, indeed. So the slides, as I mentioned, will be available on the GeoNet Departments of Transportation website that you can easily find, as well as then the entire webinar will be back on our Departments of Transportation webinar series, where you can access any of the past webinars in this series and on other topics as well. Again, several other questions, just whether the slides would be available and so forth. And as I said, yes, they will. The question, so many of the state DOTs and oftentimes even some of the county departments of transportation have already, as you mentioned, collected LiDAR data for other purposes, maybe for asset inventories, pavement condition and such. So you can basically use just the basic LiDAR that they've already collected. Is that the case by and large?
Yes, that's correct. We can either use airborne LiDAR, or we can use LiDAR that's carried out from a vehicle platform. And we've got a few different ways of amalgamating that model as a composite, depending on where the LiDAR source came from. That's by and large correct, yes.
Yep. And another question was really about the quality of the LiDAR data that, the LiDAR data that you were using, do you know the accuracy levels? And
we do indeed. Yes, the LiDAR set that we used for this particular corridor was stated at 1 meter accuracy. However, the relative accuracy of all the levels relative to each other was a lot better than the stated accuracy of 1 meter. We found that anything beyond that was a coarser accuracy was not sufficient to get good quality vertical features out of the road and surrounding environment.
And look, that's a good question that you've raised there, Terry, or one of the participants has raised. So where there is good quality LiDAR, this product certainly works. Where the LiDAR quality is coarser, this product won't be as effective in the area. But what we do know is that globally, people are investing in collecting high quality LiDAR for a wide range of other transport, roading, other activities not even associated with transport necessarily. So this information is becoming available, and we're identifying an application for it that adds value to the data, that requires no additional data collection for any road controlling authority. So if the data is available, this analysis can be undertaken.
Okay. There was another question about how you obtained the terrain data. Was that also from LiDAR, or how did you collect how did you generate the terrain data?
So the terrain data that we got our hands on was publicly available in New Zealand through a government department source called LINS, and the terrain itself is served up to us as digital service models or in some instances elevation models. Right. But it's just the LiDAR itself. It's triangulated or built into a surface mesh for the ground.
Okay. And another question, is there a minimum point per meter for the LiDAR? And I don't know if
Yes, I can answer that.
Yep. Okay.
So the digital surface model files that we procured from the government source LINS for this had basically a sampling frequency of each pixel on the raster surface tile is equal to 1 meter.
Okay.
So that would be a sensible minimum for looking at it in plan view.
Okay, perfect. As I mentioned, my experience, most of the departments of transportation, the state departments of transportation already have, first off, they have the relatively high accuracy street centerline files. They've actually been out collecting LiDAR data. There is publicly available digital terrain data. Do you have a sense on the terrain data, the level of accuracy that you do need on that, or? And I guess
not as important for this particular
okay.
For this particular model.
So my sense is that most DOTs probably already have much of the, if not 100% of the data that would actually be needed for this type of analysis. And how long does it take you to actually run the analysis for? You did it for what, a county, and how long does a county take to really run?
So this particular corridor that we chose was around the 20k mark, 25.
20. It's about a 15-mile stretch of that corridor that we demonstrated there.
Yep.
That one there was specifically chosen by the New Zealand Transport Agency, or in conjunction with them, because it is a corridor where the vertical undulations are quite subtle, and we wanted to test the model in an environment where we have subtle vertical changes in grade, because obviously the model doesn't need to be particularly fine grain if we're dealing with mountainous terrain. It's very obvious. So we were dealing with a flat to rolling terrain where there are very subtle changes in vertical grade, so we could demonstrate the high level of accuracy that the model was able to replicate. In terms of effort to generate that 15-mile corridor, I think it was probably around a week, Andrew, to do that. But at the same time, we were still undergoing a number of enhancements and validation for actually running the model. Now that we've got the model validated, it can certainly be a lot faster. Andrew, you got something to add to that?
So I guess possibly the intent of the original question was, what's the run time of the model over that particular stretch of road? Now, for that corridor, it was approximately 25 minutes to assess both directions. And we haven't employed a high level of processing power or parallelism in that particular run. So with some optimization or with leveraging a bit more cloud computing, we'd certainly be able to drop that time down.
Right. And another question, what's the error between the field data and the model data? So I guess that would really go back to your validation. What were your validation results?
In the examples given there, and speaking firsthand as I was one of the people that validated it, we didn't find any locations on that entire length of corridor that we found that the model was giving us false positives, and we did find some areas that, as shown in the images, were clearly should have been marked for no overtaking under New Zealand's marking policy. We don't have a margin of error as a specific value that we know of yet. We could do a study over the results, and we'd probably need high precision data on the corridor itself to be able to give you an answer to that. But with broad strokes, we'd say that it is very close to resembling reality.
One of the benefits here, Terry and others, is that at the moment, road controlling authorities don't have a tool that allows them to audit the accuracy of the no overtaking lines that are placed on their network. This is a tool that allows for that auditing to take place and to say, have we captured all of the no overtaking opportunities, no overtaking areas on the network that should be in place? And on this corridor here, as Andrew said, all of the areas that were marked with no overtaking were verified through the model. However, our model did identify other areas where visibility is lost and there should have been further no overtaking lines introduced. And I believe while you were on site, Andrew, witnessed a very unsafe overtaking manoeuvre from probably a tourist, a visiting driver, unfamiliar with the road, who was in a camper van, overtaking along a section of road where there was no overtaking lines marked, and there was clearly a lack of forward visibility ahead due to a very subtle change in vertical alignment. And if there was a vehicle heading in the other direction, that could have resulted in a very bad outcome through a crash on that corridor. So that's the real benefit here in terms of not just where should the lines be installed, no overtaking lines, but also creating an audit process for verifying if what you have marked on the road corridor is actually representative of what should be out there.
And we've also spent some time looking at what you can do to improve that visibility on the edges or outside the road reserve into, in this example, would be rural farmers' properties. If they had large areas of trees or overgrowth that were along the edges of the road reserve and you were very, very close to achieving your site distance threshold, how you as a transport authority could work with that landowner to try and reduce the amount of overgrowth and items that would impair visibility through those sight lines to make the corridor safer.
We're also using this now to identify strategies for creating other safe passing opportunities along corridors. So identifying strategies for slow vehicle bays, pullover areas, formalised passing lanes, and the like. So this is a model that allows you to assess what the frequency of passing opportunities is like along the corridor, and then you can run some mathematical analyses to work out the likelihood of there being a vehicle heading in the opposing direction when there is safe passing, to effectively say what proportion of your journey time along the corridor might you have safe passing opportunities. Does that sit above or below the threshold that you're looking for that function of road? And then that information is used to inform a strategy around the need for additional passing facilities.
Yeah, and you did, I believe, mention that based on this work that it's really sort of initiated a discussion, reevaluation among the New Zealand Transport Authority on precisely their own methodology and their own marking system. Is that correct? And are they what's been the response, I guess? Are they looking at this as a way of really sort of changing their methodology?
Yeah, look, that's a good question. So there's two components to it. There's one, this is a verification and audit tool of what they have out there under their current policy, whether or not it's accurate or not. And secondly, exploring changing the policy around the provision of no overtaking markings to include forward visibility being lost due to horizontal curvature only. That's not part of the New Zealand policy at the moment, but this tool is being used to evaluate the implications of that. And one of the implications is not necessarily just the marking of the curves, but full visibility, or 1,000 feet of visibility, needs to be re-established in order for the no overtaking lines to terminate. And so if you start a no overtaking line, that may end up heading along a corridor for a very extensive length afterwards, and the Transport Agency, in conjunction with other partners such as the Automobile Association, really want to understand what the implications of that are on passing opportunities along across a road network. So we're working with the agency on that.
Okay, yeah. All right, well, I think we'll give a couple more seconds or minutes here for any more questions, but again, really impressive, both the first part of the presentation in terms of really being able to bring together multiple data sets in ways that help the safety analyst better understand the risk, and then what would be the most likely countermeasures, and really being able to look at the return on investment on that. I know that that's certainly a key focus of safety analysis here in the States as well, that how can we understand the most effective and most strategic countermeasures based on the infrastructure of the roadway, and how do we prioritize those countermeasures that have the highest return on investment, as a way of doing a prioritization of where we spend the limited amounts of highway safety infrastructure funding. So, and then the second is really quite amazing. When you told me a couple of weeks ago that you had developed this, it's much more impressive and very nicely done. Actually, I think it could actually become quite a valuable tool for road agencies. So I'm not seeing any more questions, so we'll go ahead and we'll wrap it up. As I mentioned, this recording will be up on our website probably sometime early next week, and the slides for this as well will be on the GeoNet Departments of Transportation website. We do thank you all for attending today. If you do have any follow-on questions, both mine and Paul's emails are on the screen. And we hope that all of you have a nice Thanksgiving. And again, thanks for attending our webinar. Okay, bye-bye.